Hello guys, and welcome back to Engineering Hack, where we try to solve engineering problems in a way that's hopefully easy to understand. Today we're in the domain of thermodynamics, and we have a problem with not one but two turbines. We have a video in this channel already solving this exact problem, and we're just redoing it so that we're now doing it with the higher quality, better audio, and with the tablet. So what we have here is a turbine that has steam going into it and then it's outputting some work. But then afterwards, the output of this first turbine, some of it is expelled, put it that way, wasted, and some of it is actually directed into a second turbine, which is then going to release some extra work and spit out a fluid of even lower energy, right? So what we have here is work being outputted by this first one and the second one. All we need to do is calculate them individually, sum them up to find out what is the total work for the whole system. So if that's what you need to be able to solve it, just go ahead and do it by yourself. If you need some extra help, let's do it together. So the problem statement reads for problem 5.52, steam enters a steady flow turbine with a mass flow rate of 13 kilograms per second at 600 degrees Celsius and 8 megapascals. We know already just by doing so many of these as this has to be superheated, but we're going to check anyways. A negligible velocity. The steam expands in a two-stage adiabatic turbine. In the first turbine, the steam expands to a saturated vapor at 300 kilopascals, where 10% of the steam is removed for some other use. The remainder of the steam continues to expand. The second turbine exits where the pressure is 10 kilopascals and the quality is 85%. Determine the power output of the turbine. So power output of the combination of these two guys here, that's what it wants. It wants power, so we're going to be after something in the units of watts, right? Power, so joules per second. We are dealing with steam, so steam tables are going to be handy in this problem. What else? Steady flow. This is important. Steady flow, right? What does that mean? It means that whatever the mass that's entering, in this case here we have 13 kilograms per second, that's going to be always the case, right? We're not going to have 13 kilograms per second changing over time, or just 13 kilograms per second over 1 minute, something like that. No, it's just 13 kilograms per second forever. We have the two properties, set of properties for the first state. That's great. So this state is completely defined. We can grab whatever thermodynamic property we need for that state. We are considering our velocity to be negligible. What does that mean? We are ignoring the kinetic energy. Steam expands in two stages. Adiabatic turbine, another important word. Why is that? Because that means that there's no heat being lost, right? In these turbines, I should say, right? No heat being lost. In the first turbine, the steam expands to saturated vapor. So again, we have everything we need for the second state. We know it's a saturated vapor, and we know it's at 300 kilopascals. So all we need to do is go through the 300 kilopascals in the table and then grab properties for saturated vapor. Where 10% of the steam is removed for some other use. So this is new, right? So now the second guy, as we were talking about before, we have 10% of the mass going down this way and 90% of the mass going down that way. So why is that important? Because this means that the mass, the 13 kilograms going through the first turbine, are not going to be exactly the same as the ones going through the second one. It's going to be just 90% of that 13 kilograms on the second turbine here, right? So that's relevant because we know the mass flow rate is related to the power output of this guy. The remainder of the steam continues to expand to a second where the exit pressure is 10 kilopascals and the quality is 85%. So this is yet another valuable information. We have the pressure and we know there's a quality. If there's a quality, there's a mixture, saturated mixture. 85% is steam. The other 15% is liquid, right? Saturated liquid. So we have everything we need, right? Really. We have the two set of properties of this guy here. We have the two things we need over here. And we have the two things we need for the first state. So as simple as that, we can start figuring out our problem. So let's do our turbine number 1 here. Turbine 1. We're going to have turbine 2 over here. The power output of these guys is the combination of the two powers going on here. We go have let's just draw energies and masses, right? So mass, energies in blue, and then we have masses in green. And we have something going like so, something going like so. Okay, so we have the enthalpy 1 going in for the first turbine, and then it's leaving enthalpy 2, and enthalpy 2 is also going into our second turbine. Then we have enthalpy 3 leaving, state 3 that is. And in terms of mass, we have mass flow rate 1 going in here. Then we have 10% of mass flow rate 1 leaving this turbine, and we have 90% of mass flow rate 2 going in there. And then because we can destroy the mass, we also have to have 90% of the mass 1 going in, leaving our second turbine. That's what we have in terms of energies, right? Let's probably break this down even further and do this. So let's do this. It's less confusing. So enthalpy 2 is leaving over here, and this is related to 90% of mass flow rate 1. Right? It just happens so to be that this guy is also going into that guy there. Right? So this is what's going on. There's no heat whatsoever. So this is the breakdown. So what I'm going to do is we're going to do energy balances on both these turbines, right? The first and the second turbine. We can go ahead and calculate what's going to be this 90% here, because this is just 90%. So 90% of M1 equals 11.7 kilograms per second. So we need to remember that whenever we're calculating anything for the second turbine, it has to be 11.7. And everything for the first turbine is going to be 13 kilograms per second. So let's just put, it down here. Beautiful. Okay, cool. So let's start by doing the energy balance on the first turbine. Let me go ahead and copy this. And we're going to say, you know what, whatever is happening here, energy has to be conserved, right? Oh, and also obviously big part of this whole thing is output of work, right? So let's call output of work 2 for turbine 2 and output of work 1 for turbine 1. It's the whole point of using a turbine, right? We put some energy in, we want to get some work out of it. So if this is the case, what's going in is enthalpy 1, energy-wise, right? It's enthalpy 1 is what going in. What's coming out of it is enthalpy 2 and the work, right? So that means that if I do an energy balance, this means that enthalpy 1 plus kinetic energy 1. Oh, we can do the whole thing, right? So internal energy, flow energy, kinetic energy, potential energy has to be equal to the same thing on the other side. We're ignoring potential energy, ignoring kinetic energy, potential energy. The combination of these two guys is enthalpy. So therefore, we end up with enthalpy 1 minus what's going out, enthalpy 2 minus work is coming out has to be 0. Or in other words, enthalpy 1 has to be equal to enthalpy 2 plus work. Work of turbine 1, that is. Okay. Now, question that I get in class sometimes. Don't I have to account for the enthalpy 2 twice? Well, it depends, right? If you're telling me that you're going to account for enthalpy 2 considering 10% of the mass, and then enthalpy 2 again considering 90% of the mass, yeah, of course. You're going to consider it twice, but then it's 90% of the mass and 10% of the mass. So if you combine the two things, what you're doing really is you're considering all the energy as one time. So you can do what you're going to be doing mathematically is exactly the same thing. Let's just do it for the sake of visualizing. All right. So what you can do is, okay, I'm going to have 90% of H2 plus 10% of H2 plus work 1. Okay. 90% plus 10%, that's 100%. So exactly the same thing as doing this. No changes whatsoever. Right. Now, don't forget that we're not interested in the pure energy states because we're interested in the rate, right? This is a rate. This is not happening. It's not, a snapshot in time. This is actually happening constantly because we have a steady flow situation. So we're interested in the flow at which the enthalpy 1 is going into the turbine, the flow at which enthalpy 2 is leaving the turbine, and the flow at which work is being outputted. So we're not interested in this. We're interested in reality in mass flow rate 1 times H1 mass flow rate 1 times H2 plus mass flow rate 1 times work 1. That's going to give us the power of every single thing instead of the energy per se. They're all in one, so it doesn't really matter here at this point in time, except that we want this, so that's why we need to consider the mass flow rate. So you can't ignore it for now and just consider this guy. Oops, what did I do? There you go. So what you can do is just consider this bit here, and let's find out this fella here. Once we have that fella, we can multiply by the mass flow rate to find out what's the power of state 1, right? So really what we're after is, what is the energy output of work output, of turbine 1, which is just going to be H1 minus H2. Once we do that, then we go ahead and say, okay, beautiful. If I multiply the work output 1 by mass flow rate 1, I'm going to get the power output of turbine 1. And then I rinse and repeat that for turbine 2, sum the two things up. That's my game plan for solving this question. Let's put this down. This is step 1. Step 2. Step 3 is what is work output 2. And then step 4 will be what is power of turbine 2. And step 5 is total power, which is power of 1 plus power of 2. That's the game plan here.